We know that the conversion of a ketone to a secondary alcohol is a reduction reaction from our lessons on identifying oxidations and reductions. But what reagent are we going to use to carry out this reduction? And I want to approach this problem by thinking about what sort of reagent you will need. Let's think about what must happen mechanistically when a ketone is reduced to a secondary alcohol. And I have a clue here on the structure. We need to add two hydrogens, indicated in blue, across the carbon-oxygen double bond. So we most commonly see hydrogen atoms introduced as H+. And in fact, the hydrogen that ends up on the oxygen in this product can and will come in as H+. But the hydrogen that will bond to carbon must come in as H- in order to react as a nucleophile with the electrophilic carbonyl carbon. So what do we know about H-? Well, first of all, we know that it has a negative charge in a lone pair. But H- is the conjugate base of H2. The pKa of H2 is 35, so H- will be a very strong base. If we react a ketone with sodium hydride, which would be the chemical source of H-, we will actually not get the reactivity that we want, because sodium hydride will behave as a base rather than as a nucleophile and remove one of the alpha hydrogens to form the enolate. Okay, we don't usually use this base to form an enolate, but it actually will do that, and you are already familiar a little bit with the generation and reactivity of enolates from earlier lessons. So just like there is a tamed down nucleophilic form of R3C-, namely the Grignard reagent, there is also a tamed down nucleophilic form of H-, namely NaBH4 or sodium borohydride. Okay, so now I'm throwing boron into the picture. Well, this reagent was discovered by an American chemist named H.C. Brown, who won the 1979 Nobel Prize in Chemistry for the discovery of reactions that incorporate boron as reagents for organic synthesis. He actually became interested in boron, as the story goes, when his girlfriend at the time wanted to give him a book as a birthday present back in the Great Depression, and the only book on chemistry that she could find was a book on boron. He read it and got so enthralled in the subject that he spent his entire career researching the chemistry of boron and its relation to organic compounds. So why does this work? Well, the answer is that boron is less electronegative than hydrogen is, so the boron-hydrogen bond is polarized B plus H minus. Just like in the Grignard reagent, the magnesium-carbon bond is polarized magnesium plus carbon minus. So therefore, sodium borohydride is a source of H minus, just like the Grignard reagent is a source of C minus. Okay, so let's look at an example. We already saw on the last slide a ketone being reduced to a secondary alcohol. So here we'll look at the reduction of an aldehyde to a primary alcohol. So acetaldehyde in this case reacted with sodium borohydride in ethanol as a solvent. I'll get to why that's important in a second. Will give us ethanol as the product in this case. Okay, so let's look at the mechanism, and the mechanism of this reduction is very similar to that of the Grignard reaction. So the carbonyl group of the ketone and the sodium borohydride will approach each other such that their dipoles attract. Okay, so the boron is the positively charged end of the BH dipole. Now you're going to think I'm nuts because I stuck a negative charge on that boron. A boron forming 4 bonds has to have a negative charge because of the formal charge rules. This is where the formal charge rules become a little less useful for predicting reactivity. But as I said, the boron is the positive end of the dipole, and it's attracted to the oxygen, which is the negative end of the carbonyl dipole. The hydrogen, which is the negative end of the BH dipole, approaches the carbonyl carbon. So we have our two arrows, one going from the boron-hydrogen bond to the carbonyl carbon, and then another arrow from the carbonyl CO pi bond to boron, which ends up forming a boron-oxygen bond. Okay, so we've transferred our hydrogen to the carbonyl carbon, and we now have this BH3 group sitting on the oxygen. The only thing standing in between this intermediate and the final product is getting rid of the boron and replacing it with a hydrogen, and this hydrogen can come as H+. Now, we don't have H+ per se in the reaction mixture, because if we did, it would react with the borohydride, generate H2 gas, and you wouldn't have any more borohydride left. But what we do have is ethanol in the reaction, and it can act as a source of H+. Okay? Just like water can act as a source of H+ in the aqueous workup phase of a Grignard or epoxide reaction. So we add our arrows. The boron-oxygen bond picks up the hydrogen, thus the hydrogen gets bound to the oxygen. Those electrons are used to pick up the hydrogen. And then you break the hydrogen-oxygen bond, putting the electrons onto the oxygen, and then we end up making ethoxide, which in the end ends up reacting with the BH3 that would otherwise be lost. And those two will react together to prevent there being a strong Lewis acid BH3. But that's a little bit tangential to the scope of this mechanism. But what you need to know that's important is that ethanol, which is the solvent for this reaction, is also the source of the proton in the second step. Okay, so that ends our mini unit on oxidation and reduction organic chemistry. So what you know now is how to assign oxidation state to a carbon, how to identify whether a reaction is an oxidation, a reduction, or neither. You know the reagents capable of oxidizing primary or secondary alcohols up to carbonyl compounds. And then finally, in this lesson, we know the reagent that we use to reduce a carbonyl compound down to an alcohol.